All right, section 7.2 is one-to-one and onto functions, and as well as inverse functions. Now I know we've all seen all three of these things before, at least once in your algebra days and in pre-calculus. We have four things we're going to talk about. First is review our definitions. So one-to-one definitions, one-to-one, and onto definitions. And just like in the last section, I know that we know what these things are. We're going to update the definitions and think about them from a set theory perspective. And then we're going to talk about those one-to-one, one-to-one, and onto functions on sets. And that's going to come down to how do we prove that a function is one-to-one or onto given two codomain and domain sets. We're going to talk a little bit about one-to-one correspondences. Correspondences. What that definition means. And then you can't talk about one-to-one functions without talking about inverses, and one-to-one functions. So starting out with our definition of one-to-one. We're going to let f map x into y be a function f is one-to-one if and only if for all x1 and x2 in x, if f of x1 equals f of x2, then x1 equals x2, or by contrapositives, if x1 does not equal x2, then f of x1 does not equal f of x2. So these two statements are equivalent. We're just using contrapositives here to give us two avenues. Now, primarily we use this first property, f of x1 equals f of x2, means that x1 equals x2, to prove that a function is one-to-one. Now, we typically don't use the terminology one-to-one moving forward. A function that is one-to-one that is one-to-one is called injective. And this process of proving it's one-to-one, we say, is proving a function's injectivity. So it just gives us a word plus. It's a lot easier to write injective than one-to-one over and over again, at least for me. So that's our set theory definition. It's the same definition you know from one-to-one. Every output has only one input. So if two outputs are the same, then the inputs are the same. It's just a kind of a different coding, just like our definitions in 7.1 were. And for onto, again, we're going to let f map x into y be a function and we say f is onto if and only if for all y in y, there exists an x in x such that f of x equals y. And we call a function, I need more space, we call a function that is onto we call this surjective. So we have injective functions and surjective functions. Injective means one-to-one, surjective means onto. Again, this is no different from the usual definition. Onto means that every element in your range has an element that's associated with its domain. So every element in the range, in the codomain, has an element that gets mapped to it from X, from your domain. Now, surjective functions, so this is not part of the definition, so we'll split it. So for surjective functions, we're going to use f that maps x to y. Again, the image of x equals y. So this means that your image is actually equal to your codomain. And remember, this is instead of the usual that we saw in the last section, where the image of our domain is a subset of our codomain. So there's a difference here. So surjective functions or onto functions, it means that their image is the codomain. Their range is the same thing as their image. They map to everything that's in that set. Whereas for normal functions on sets, you don't have to map to everything in your codomain. So let's take a look at how we would prove a function is one-to-one or injective. So we are going to define f to map reals to reals and g to map integers to integers by f of x equals 4x minus 1 and g of n equals n squared. So the question we're going to ask is f of x or g of n injective? Prove or give a counterexample. Counterexample. So knowing what we know from our algebra days, this is a linear function. It's a linear function on the real numbers. We should be fairly confident in the fact that this is indeed one-to-one. It's injective. So we need to go about proving it. And so the way that we prove that a function is one-to-one is satisfying that definition that we have. And I'm going to use this first property right here. So I'm going to allow two elements to have their function values be the same thing, and I need to prove that those elements then need to be the same number. So it's a lot simpler than it sounds. So we are going to suppose that x1 and x2 are real numbers. Next, we're going to assume that f of x1 equals f of x2. So that means that, according to our function definition, 4x1 minus 1 equals 4x2 minus 1. Add 1, 4x1 equals 4x2. Divide by 2, divide by 4. And we have that x1 equals x2. And that's what we wanted. So this is how most of these proofs for injectivity go, is you let your x1 and x2 be elements of whatever your domain is. Then you assume that f of x1 equals f of x2, whatever your rule is. Use that to rewrite f of x1 and f of x2, and then solve it, and simplify. And then you should come to the same conclusion, excuse me, that x1 and x2 are the same. And so since we have that, we can say, therefore, f of x is injective. Now, for g, this is the quadratic. You can think of it just like x squared. We know the quadratic itself is not one-to-one. It would fail that horizontal line test. So our counterexample, since we're limited to integers, needs to come up with two integers that have the same function value. That's easy enough since it's the quadratic. So our counterexample of g of n not being injective well, let n equal a, any integer, and then we know that g of n equals n squared, and g of negative n, well, that's negative a squared, which equals a squared, which equals n squared. And so we have g of a equals g of negative a, and a certainly does not equal negative a. And you can pick any integer a that you want. And this is exactly what we know. When we have that quadratic, it's going to fail the horizontal line test anywhere we choose through that parabola. And so that's how we want to be thinking about injectivity, just like you did back in your algebra days. Does it pass the horizontal line test or not? And you can use things that you know. You know that odd functions typically are one-to-one, and even functions for polynomials typically not. You just have to figure out how to prove it, how to write it up properly. And this is how most of your proofs and counterexamples are going to go. So let's take a look at an example of surjectivity then. So we are going to define f to be the function that maps reals to reals, and g, now let's use h. Let's change it up. We'll map integers into integers by f of x equals 4x minus 1, and h of n will equal 4n minus 1. And we want to know, are either of these, are either f or h surjective prove or give a counterexample. Counterexample. Long word. So, if we start with f of x, again, we have this nice linear function. You can think of the line. You could think, is there any real number that we can't actually be equal to? And the answer we know should be no. It's a line. It should hit everything. So we need to go about proving that. So we are going to let y be a real number. Then, if x equals y plus 1 over 4, and since 1, 4, and y are all real numbers, x is a real number, then f of x equals 4 times y plus 1 over 4 minus 1, which equals y plus 1 minus 1, which equals y. Since y is arbitrary, this means for all y that are reals, there exists an x that's a real number, such that f of x equals y, or f is surjective. So, unlike injectivity proofs, surjectivity proofs are proofs by construction. You have to figure out what your proper element needs to be in exactly the right form, ensure that it's still in your domain, and then make sure that you can get to the generic y. Whether you have your codomain being reals or integers or rationals, you just you give a general one. In this case, I just chose y, x and y. Now, figuring this out might be harder or easier depending on the function you're given. Obviously, if you're looking at this linear function, you know that I just solved y equals 4x minus 1 for x to get the right y. Now that's all scratch work and it shouldn't show up in your proof, just like we've talked about. All the proof needs is this number, and then a sentence justifying why your x is a real number, or whatever domain you have. Since I have all real numbers, we're inducing closure here, implicitly inducing closure. We know that that's going to be a real number. And then you just show that your choice works perfectly for the y, for the general y. And you have your proof for surjectivity. So I think it splits about 50-50. Some students find surjective proofs really easy because they're just construction. You're just doing some scratch work to figure out what you need. Some students find injectivity proofs to be the easier because you have a set way to do things. Let f of x1 equal f of x2, show that x1 equals x2. There's more structure to it. But let's take a look at the important part of this example is when we change our domain or codomain, or both in this case, how we have a surjective function, but h is not surjective. So there's integers mapping to integers, and we have the line 4n minus 1. Now can you imagine to yourself, is there any integer that you can't get from this expression when all you can plug in is integers? So our counterexample of h of n being not surjective. That's terrible English, but I'm going with it. And there's one classic integer that you've been solving for your entire life in math, and that's 0. 0 is an integer. No one would argue that. But for this to be true, n would have to equal 1/4. 1/4 is not an integer. So that means that there does not exist any integer n such that h of n equals 0. So a lot of times when you're dealing with functions that their domain is only integers, 0 is going to be, again, a lot of times, not every time, but 0 is going to be the thing that you check to see if you fail. Because most integer equations, integer polynomials, when they set equal to 0, have rational solutions. Now, about half the time those are integers as well, but the other half the time they're rational, true rationals, like this 1/4. So if you're never not sure if something's surjective or not, and you don't know from previous experience, like we know 4x minus 1 is a line, we can graph that. When you start messing with the domains though, especially when you're dealing with integers, just set it equal to 0 and see if you can get 0. And if you can, okay, then you'll have to start thinking about some other things. But if you can't, you've got your contradiction, your counterexample right there. So a couple quick things to note that we're not going to prove here, but you'll need in your homework for a few problems, is that the exponential and logarithmic functions are both one-to-one or injective and onto or surjective. So if I remember correctly, you might have to prove that one of these is injective and surjective, or maybe both, but it's the exact same type of proofs that we just outlined in the last two examples. So because we know that the exponential and logarithm functions are inverses of each other, you're going to be using that result for your onto proof. And the injective proof, if you do it just like we did in the example, it'll go with no problems. So let's talk about one-to-one correspondences. So a one-to-one correspondence is a bijection. And so you may have guessed that this means it is injective and surjective. And both of them. So a lot of times we're not going to call it a one-to-one correspondence, we're just going to call it a bijection. And if we call something a bijection, that means that it's both injective and surjective. And so now a common question that we can be asked is to just prove that a given function is a bijection. So let's look at an example here. Let's do a little bit different function. So let's map R2 into R2 with f, and not and. This means, just a little review here, R2 is the Cartesian product of R cross R, so f maps R cross R into R cross R. So our elements are ordered pairs, x comma y's, and this would be by our function f of x comma y equals x plus y comma x minus y. So the first thing we want to think about is this bijective, or where you're going to prove this is a bijection. So I like to start bijective proofs with scratch work. Remember the proof, we write proof to indicate where our proof begins. And so whoever's looking at your work knows that the rest of it was scratch work of how you justify to yourself. So we can just look at f of x1, y1 equals f of x2, y2. All right, remember, we're not proving anything right now. We're just seeing what this would mean. So that means that this is f of xy is x plus y, so this is x1 plus y1, comma, x1 minus y1 has to equal x2 plus y2, comma, x2 minus y2. And we know from our study of ordered pairs that for two ordered pairs to be the same, x1 plus y1 has to equal x2 plus y2, and x1 minus y1 has to equal x2 minus y2. So we have two equations and two unknowns. This is a linear system, so I'm just going to add these up. We're going to get 2x1 has to equal 2x2, so x1 has to equal x2, and then plugging that back into our equations, or we can just do the first one really. So we take this first equation, x1 plus y1 has to equal x2 plus y2. That means x1 plus y1 has to equal x1 plus y2. And that means that y1 equals y2 if we subtract that x1 from both sides. Wow, I went right through my equation there. Okay, so definitely true for that first equation. The second one, x1 minus y1 equals x2 minus y2. x1 minus y1 has to equal, using this substitution, x1 minus y2. Again, minus that x1 minus y1 equals minus y2. Divide by negative. Same result in both. So we know that this is true. So our proof is basically going to be copying this down. So we can even adjust this, but we'll rewrite it so it looks nicer. But this was the scratch work, and you can always start this to see. You don't have to write proof and lock yourself into a proof and write it formally until you know it's true. So for injectivity, this is where the scratch work is, or that was injectivity. For surjectivity, this is where scratch work becomes really important. So we're just going to let xy be an element of R2, and we need to find I'm going to use different letters to set it apart, the R and S, such that f of rs equals x comma y. Well, f of rs would be r plus s, r minus s, and this has to equal x comma y. So this means x equals r plus s, and y equals r minus s. And if I add these up, that means that x plus y has to equal 2r. And so r is going to equal, you guessed it, x plus y over 2. And if r equals x plus y over 2, well, we can swap back in to get s, or we can come over here, r plus s, y equals r minus s, and instead of adding them, we'll subtract them. And if we subtract, that's going to make the s positive, so we'll have 2s equals x minus y, and therefore s equals x minus y over 2. So again, this is all scratch work, but now we have our S and our R that we need. So in the last example I just told you, x was 4 plus y, or 4 y plus 1 over 4, or y minus 1 over 4, whatever it was. You have to do this scratch work to get it. This, again, not part of our proof though, because our proof just cares about these. It doesn't care about how we figure it out. So this all comes off to the side on your scratch work before your proof starts. So now, if we prove, or if we want to start our proof, we're going to let x1 comma y1 and x2 comma y2 be elements of R2, and then we're going to assume that f of x1 comma y1 equals f of x2 comma y2. This means that x1 plus y1 comma x1 minus y1 equals x2 plus y2 comma x2 minus y2. And by definition of ordered pairs, x1 plus y1 equals x2 plus y2, and x1 minus y1 equals x2 minus y2. Adding these equations, yields that x1 equals x2, because the y's will cancel. And substituting back into both, we have x1 plus y1 equals x1 plus y2, and x1 minus y1 equals x1 minus y2. This, as we know, gives us y1 equals y2. This gives us negative y1 equals negative y2, or y1 equals y2. So x1 equals x1, or x2, and in both cases, y1 equals y2. So by definition of ordered pairs, x1 comma y1 equals x2 comma y2, because the components of our ordered pairs are the same. That's what definition of ordered pairs says. Two ordered pairs are the same if their components are the same. And therefore, f that maps R2 to R2 by f of xy, I don't know, space here, f of xy equals x plus y comma x minus y is injective. Okay, so our goal of this proof is not to prove just injectivity and surjectivity, so we can combine both proofs into one and just start with now let x comma y be an element of R2. Notice I'm even being very careful here that I'm not using x1, y1, since I'm still technically in the same proof. We don't want to overlap variables. So xy is an element of R2, and we're going to let this be arbitrary. if r comma s equals x plus y over 2 comma x minus y over 2, then capital F of r comma s equals x plus y over 2 plus x minus y over 2 comma x plus y over 2 minus x minus y over 2, which is going to be x plus y plus x minus y, or 2x over 2, comma 2y over 2, which equals x comma y. And since x comma y was arbitrary, it follows for all x comma y in R2, there exists an r comma s in R2 such that f of rs equals x comma y. Therefore, f is surjective. And the last part, since f is injective and surjective, we can say f is a bijection. Which is the ultimate end of our proof. So we have to prove injectivity and surjectivity all at the same time. And that's the end of our proof. So there's a good amount of work that you have to do when you're proving bijections, because you want to do your scratch work first to make sure you understand how your proofs should work, or what cases are going to disprove them. What are your counterexamples? There's 2 more theorems out of this section that we're just going to write down, and I'm only going to write them. We're not going to prove them, and you can use them in your homework for free without having to prove them, because these are things we already know are true from previous courses. So the first theorem is a function f that maps x into y is invertible if and only if f is 1-to-1, or injective is our new term. And we know that from algebra. We did the horizontal line test to show that a function had an inverse. And so this equates to saying that f inverse that maps y into x exists if and only if f that maps x into y is injective. So proving that something is invertible or that its inverse exists, you prove injectivity first, and you say since the function is injective, it's invertible or it has an inverse. This also means since this is a pre-image, technically, you can think of the pre-image of this, you won't ever look at pre-images unless you are injective, because you can't go backwards. And the second theorem here to end this section is if f that maps x into y is a bijection, then since bijection means injective and surjective, that means that f inverse that maps y into x, not only does it exist, it is also, whoops, I don't need an it, is also a bijection. Because if everything in x maps perfectly to everything in y, when you follow these paths backwards, everything here has to map perfectly to x. So yeah, I don't think you have to prove this in the homework, but maybe you do. I won't hold myself to that. But it's as simple as you have a bijection, so you know that you have your inverse, and then it's just showing that this function maps bijectively back into y into x. And that's it. So again, these are two theorems. You can use them in your homework. If you have to prove them, prove them. But if you need them for another problem, please do use them. This is the end of 7.2, though.